Good afternoon, everybody. I want to thank you all for coming to this week's Virtual Simulation Lab seminar. Today we have a very interesting topic, which is probably great importance to a lot of people here at the IKP, especially those working in the sub-pro. There's a lot of interest in this topic. This is Modelica. This is a language that we use to build models, and it's got a few nice features which make it especially attractive for building chemical process models. Today we have Julian Straus here from the IKP, the Process Systems Group, and he has developed enough expertise in Modelica in order to come and give us a basic idea how to get started with it and what are the important things that you need to know in order to start working with it. So, without any more time wasted, I give you Julian, and I hope we have a nice lecture today.
Hello, as Brian said, I'm Julian. I'm working with the SIGA as supervisor, and I'm going to talk today about the language Modelica with the user interface Dymola. Adriana Reyes-Lua originally should have also worked with me in this presentation because we went together on a Modelica course. However, she's this week in Hammerfest and was just able to help me to prepare the presentation. So, first I'd like to talk with you about the structure and want to explain you what is Modelica. Because, I mean, you need to have a basic idea of what I'm talking to you afterwards. Then I will explain in a few minutes the Dymola environment, because the program I will explain to you is Dymola. Then I will introduce you to the concept of class, which is for object-oriented languages quite crucial to understand, because if you don't understand what a class is or what the different classes do, it's hard to make a really nice model. And these concepts of class I will explain to you on a model system. And the model system is a simple valve. And with this valve we go through a connector, the model itself, and inheritance and polymorphism, which is a really nice feature of Modelica itself. And finally to aggregation and flowsheet development, which is essentially the point why I initially decided to go for Modelica. And finally, I will show you what I did, and that is the Armenia synthesis gas loop, a simplified loop built from the scratch by myself. And it's just an example what you can do with Modelica to build up. It's not really a big flow sheet, but bigger flow sheets. Okay, but now the first question is, what is Modelica? The Modelica Foundation had a nice description online, and they say it's a non-proprietary, object-oriented, equation-based language. Crucial part here to note is it's a language. So there are multiple graphical user interfaces you can use to, or where you can define Modelica. And the reason why I initially choose to go for Modelica is that it's a nice way to reuse the models you already designed. For example, in my case, I have to work a lot with heat exchangers, 3 compressors. And in MATLAB, that is kind of annoying. In Modelica, it's really nice to reuse a model you made and to connect models to a flow sheet. It's kind of working like HYSYS or Aspen Plus in terms of a flow sheeting software to build up a big flow sheet. It's Modelica Association, so that was wrong. So, what can we do with Modelica? It has a graphical modeling interface. So, compared to MATLAB, you don't have to write all your equations down and have to think, okay, did I now connect that with this variable? Which part of my states is now here and which is there? It's graphical. It's quite easy. You just draw it with your mouse. You can compile it, or the whole Modelica environment is symbolic by definition. So if you have a big system, Dymola itself, as an example, simplifies the system for you. So it does a transformation and it allows you to easier get the solution afterwards. And for simulation, it's working like a numerical integrator or it is a numerical integrator in a flowsheet solver. Now, you probably will ask yourself, that is something you can also get with a Simulink, but you will see afterwards where the advantages of Modelica lie. Crucial again to notice, Modelica is only the language, but there are several commercial softwares which are applying Modelica. We are using Dymola now today, which is one of the biggest Modelica software and where it originally comes from. And however, you can also go for MapleSim, Simulation X. Each of these have their advantages and disadvantages. At least I've been told that. I haven't used the other ones. And you can somehow imagine it that Modelica is like the LaTeX language, and the different softwares like Dymola, Simulation X, is then the graphical user interface, like for LaTeX on Windows computers, Technic Center or TechMaker. They all have the same underlying syntax, but have a different interface for you to use. Obviously, there are also open software, which is OpenModelica and JModelica. JModelica is from Lund University, and that's also where Modelica originally comes from. So, coming again, why should you use Modelica? The advantage of Modelica is you don't have an assignment statement. Everything is based in equations. So the left side does not have to of an equation does not have to consist of only one variable. You can have an equation which is complicated to solve for one equation, for one variable. You just write it in the complicated form. You don't have to solve different quadratic or any other polynomial equation for a variable. You just write it in the way you have it, and Modelica gets it for itself. You have flow directionalities, which is now the opposite what you have in Simulink. In Simulink, you only have information flow. So the flow is defined, the direction. In Modelica, you have a real, actual flow, and it calculates everything based on a flow. And you have a really nice hierarchic building of the models. And that is, in my opinion, the nicest thing about Modelica. It's object-orientated. I'm not sure how many of you have used object-orientated languages so far. For me, it was the first time when I went to the workshop, and there it's again nice. You just define once a model, and then you get it, use it 5 times, 100 times, no one cares. If you have, for example, for a heat exchanger, different models, one is a simple logarithmic mean temperature difference heat exchanger, the other one is a detailed model, you can just exchange them, and you don't have to change anything in the structure. And what written with the nice word extensible, you can just build up hierarchies. So the basic stock, for example, like a pressure drop equation, which is, if you say it's always the same for heat exchanger or a valve or a reactor, that is something you only have to code once, and then you can load it in each of your different models. So that is meant with extensible, which is kind of a hierarchic level of the Modelica language. And this one here is just examples what you can do. Modelica is not only used by the process industry. We met at the workshop guys from Miele, German company for refrigerators. Also a guy working for Mercedes-Benz, Volkswagen. So you can't only use it for thermal systems, but also for mechanical systems or electrical engineering. And that's quite nice to use. So, but now I talked quite a lot about Modelica, and now we will just take a look at the Dymola interface. This is in general how, where's my mouse? How Dymola looks. It's quite a simple, or nah, it does not really look simple. On the left hand, we have packages. What that is, data. And here we just have a big window. And if we now go, for example, for an existing package, on the Modelica, we can go for fluids and a valve, because we are in the end interested in a valve. You can see here quite a lot of code in a really nice different colors. I'm pretty sure in the last row you can't see anything, but that does not matter. Essentially what I want to show you now is you have 3 different ways to look at it. This one here on the top left, let's use both here, is an icon. If you go for a flow sheet, this is how it looks like in the flow sheet. So you can see it. The second one here shows you what other models are you using in this model. So that is something which is crucial to know. And the third one, which we were initially, was a code. You can see you can go really detailed valve, but that is not what we want to model. Instead, we're going for something easier. Okay. And now you just got a sneak peek. Probably won't remember a lot on it, but just to give you a small idea about Dymola. And now, what is a class? Everything in Modelica is a class. And the question is, what is a class? It's just something which you really have to understand if you want to learn object-oriented languages, because classes define it. And a class is the basic structure of a language like that. And the class itself contains information. And what kind of information does each class have to know? And that is quite simple. It's just variables, parameters, equations, or other classes. And other classes means in a model, you have a model, and that model can contain models, and so on. Sounds really interesting. But what kind of classes do we have? We have the overall class, which is just saying class. Then we have specialized classes, which have, on the one hand, restrictions, but also improvements compared to the general class. And these you can see here in this table. We will later on take a close look at the connector and model class, as well as the package. But these are just other classes you can know and which you can find online what they are. The function is like a function call, and type is a class which you probably will never use, because it's not really, it's for general concepts nice, but you don't have to change anything on that. Let's start now with the package, because packages have here the nice type of model library. What is a package? Oh, shit. Go to that later. Now I want to explain to you Modelica based on our model system, the valve. We have a simple valve with a pressure drop, which is given of the square, which is normally based on Sigurd's book, the pressure drop with a constant temperature. Not really applicable here, but we just use it, and essentially it doesn't matter what kind of equation we use. And we have a temperature balance in relationship to the pressure. I'm not sure whether you can see that that is gamma minus 1, and gamma minus 1 over gamma, or gamma is just Cp over Cv, to give you an idea. And what we want to do with this simple valve is we want to develop two models. One where we have a fixed pressure drop coefficient K, and another one where we can vary our pressure drop coefficient K. And based on this example, I will explain to you now the different kind of classes which are existing in Modelica. Let's start now with the class type package. Package is also called library, and packages contain all your models. Packages are all the models you have defined, all the variables you have defined, all constants. So it consists of models, which you will see in two more slides, of connectors, sub-packages, functions. Everything is crammed into one big package, and then based on that package you can load it. And the advantage to use package is that it's kind of a nice way to organize bigger systems. For example, if you have, like we've seen beforehand, there were 5 different models of a valve. That was in the package. The top package was Modelica. The sub-package was, first sub-package was media, second sub-package valve, and there you have the valve sorted. That is one nice way. With packages, you eliminate name conflicts. It's kind of in MATLAB, if you use structures for programming, the same applies for packages. You have always the name of the package, point, the name of the sub-package, point, and so on. So it's quite easy to name the same model or use the same variable multiple times. And with a package, it's just one file. And if I, for example, work with a purely developed library for heat exchanges, and let's say Christoph needs heat exchangers for a subpro, I just send him the package file and he has all my library, which makes it quite nice for sharing. And you've seen this here system beforehand when we were in Dymola. You have here the overall package is called Modelica. And all of these ones here are classes. Overall package Modelica, sub-packages, for example, fluid, mechanics, magnetic. And then you have models in these. Theoretically, these ones would be still sub-package, but it's easier to say it like that. And to start with that now, we want to create a package for ourselves, which is called Virtual SimLab. Let's close all existing packages, create new package. Virtual SimLab. So I create a new package which is called Virtual SimLab, and if I want to give or distribute it online to all of you, I just put up one file and you have it, and you can run all the commands which I did today again. The package system is just the package is just a library, so it's an overall system. But the most crucial part, which you have to understand, is the system of a connector. If you have multiple models and you want to transport from variables or quantities from one model to the next model, you need a connector. Because the model itself is kind of an encapsulated environment. And to build up a really nice flow sheet, you need the connector, because that is how Modelica is designed. A class type connector consists of flow variables, or you use it also because it simplifies everything. Flow variables, which uses Kirchhoff's law. I'm not sure how many of you do know Kirchhoff's law. It's mostly electrical engineering about, or you know? Perfect. But at each node, a node is just where we have, for example, 3 models connected. The sum of all flows equals 0. In our case, I use it for a mole or mass flow rate, because the mass flow rate is just always have to be constant at a node, because you don't have accumulation or it's just not existing, because you see it as an infinitesimal small point. The second important stuff in a connector is the stream prefix. Stream always need a definition of flow, and a stream defines something which is carried by this flow. So for example, if you have, in my case, I have a mixer from a recycle with a certain enthalpy and from my fresh feed. And both have different compositions. My flow would be my flow rate in moles per minute or kilograms per minute. And the stream variable is carried by my flow. So essentially that would be something like a concentration or an enthalpy, because that is defined for a certain, based on a flow in kilojoule per kilomole as enthalpy. And the stream is quite an important concept, because it also simplifies your overall doing, but that would be too much for this short lecture, so I will not really cover it. And what we do now is we define our own connector for our system. That is, again, quite simple. New connector. How do we want to call our connector? Let's just call it a port. We can see here, the blue one here is called connector. So if you have a model, it's called model. If you have a package, it's called package. So it's always named on your based on your class, and you always need an end statement. So we have a pressure drop in a valve which we define via temperature. That means we need in total 3 variables. The first one would be a real type variable, and we call it the flow. No, sorry. That is really hard to see.
It's the pressure limits.
Real, flow. Oh, sorry. I screwed it up again. Flow, real, Q. So what I define here now is a flow variable, so something where Kirchhoff's law applies, and it's a real variable. So it's a 64-bit floating point. If I want to have it as an integer, I have to define integer. If I want to have a string, it's string. So it's just a definition. So we have a flow. And in addition, we need a pressure. The pressure, in our case, is nothing which is a flow variable, because the pressure does not have to sum up to 0 at a node. The pressure is not, you could say it's carried by a system, but it's still mixing rules for the pressure do not apply, because you always have it as a node, all streams have the same pressure. Yeah, you can say. So essentially, I just define the pressure as a real type variable. And then we again have the temperature. As I do not want to go into stream, because that makes it slightly nasty, I also define the temperature as real. Oh, screw it. And yeah, it's really hard for me to see anything there, because essentially it's quite hard. No, I have extended, because I want to have extended. So what we did now, we define a connector. The connector is connecting all our different models together. But now, what is a model? No, we have a connector, but the connector also wants to have a really nice symbol, because we want to see where we have to connect streams to each other. And for that, I've shown you beforehand, this one here gives you a symbol. And what we do here is just a normal ellipse, and draw it. Give it a blue, shiny point. So that is our connector. So every time we use a connector, we see it's blue, and everything we want to connect, we go via the connector. So let's save. But of course, we do not want to just go for a connector. We also want to have models, because the connector itself does not have any equation. It's just something where we connect the models with each other. And for that, we have the class type model. You can see here in model, you have equation. Equation means that you can actually write something which makes sense. And the model has a variables and parameter section and the equation section. The variables and parameter section is here. In Modelica, every single variable you use, you have to define beforehand. You can't just say, put in the equation section a Q and say, oh, but I forgot that I have to define it. That's just not working. Gives you directly an error message. And also crucial for Dymola at least, the number of equations have to be the number of variables. Okay, let's start now with designing a model. Here. We have one thing I haven't mentioned yet is we need boundary conditions. And the boundary conditions we define first, which is just also as a model, define model, call it inlet, and the inlet, or every model we define now has a connector. So you just take the port and drag it in, and call it whatever you want to call. But keep the calling consistent. Makes it easier later on. Okay, now we have in our model inlet, we have, we have a port which is called outlet. And what you see here now is this one here. That is essentially just saying I load a port which is called outlet. And that is the same as I would not need to write port outlet. No, I did not need to pull it over. I just could have written port outlet. But it's easier if you do it like that. And in addition, what kind of boundary conditions do we have to define? We have a pressure, we have a flow, and we have a temperature. So these are the three things we have to define. And now you get to know another prefix, which is called parameter. Parameter are values which are constant during the whole simulation, but which you can easily change. And our flow rate is a real value. Parameter real Q. And if we set here now a value, we just say that is our value which is uses if you do not specify it. Let's say 1000. Then, in addition, parameter temperature. For the temperature, we just say 280 Kelvin. And the third parameter which we want to define is our pressure. And as I am working with ammonia, I like to work in medium to high pressure, so it's 130 bar. So we have defined now our pressures. However, we don't our parameters. But however, we did not connect the parameters with our port. So the port and the parameters is just existing, but doing nothing. So what we have to do now is an equation section. Oh, shit. Equation section. And in the equations, we write outlet.p equals p. And I have to correct that. Yeah, it's correct. Outlet dot t equals t. Outlet dot q equals minus q. Why a minus q? Yeah, and it has to be obviously like that. Why a minus q? Quite simple. You assume, or the flow variables are defined from the objective, from your model point of view. So if you have an inflow, it's a plus q. If you have an outflow, it's a minus q. And that is based on the so-called flow variable prefix. So we have defined inlet. Let's save it. But the inlet should look slightly nicer, and for that we just take, that's how we learned it. Oh, slightly too big. You can spend quite a lot of time just to make your models looking nice. Trust me, that is sometimes a lot of fun. We have defined an inlet. We have to define an outlet as boundary conditions, which is essentially just the same. Port, define it as inlet. Block. And that's it. Why do we don't need any equations in the outlet? Quite simple, because we just have a flow-based system, so everything it calculates based on your inlet conditions. You do not have any outlet conditions, which makes it easy for us. We define a flow pressure temperature, and otherwise we would have over-defined. But we now did that. We don't want to get now our valve, which we call basic valve. The model basic valve has to have an inlet and of course also an outlet, because each valve has the wrong one. Each valve obviously has an inlet and an outlet, because so otherwise you just would not have any flow through it. In this case, with this valve, you have it quite simple. Oh no, sorry. In this way, I define the valve as a partial model. What does partial model means? Partial model is a model which you can't use for a simulation. You can just extend it for a full model. We want to have two systems, one where we have a fixed pressure drop coefficient, one where we have a varying pressure drop coefficient. But stuff like the mass balance and the temperature balance do not change. They are the same for both cases. So we do not have to define them together. So what we do now is we have the partial model, which is equations which are for both the same. And as you probably remember, we have the constant which was called gamma, which is Cp over Cv. that is something we define now here. And here I use the value, the prefix constant. Constant is a value you just can't, or have only limited ways of changing it. It's more difficult. And I use the value for a monoatomic ideal gas. But I obviously have to put, again, constant real gamma equals 5 that. Going now to our equation section. If you recall it, we have a mass balance, which is in this case defined by inlet Q equals outlet, equals outlet Q, and again minus outlet Q, because it's based on the system. And also, which is showing you now the non-causality system, the pressure ratio, inlet P divided by outlet, am I writing correctly now? Outlet P to the power gamma minus 1 divided by gamma equals inlet T over outlet T. And in this case now, you see it really nicely that you don't, this equation here, if I want to solve for P, or for the temperature would be easy. But if I want to solve for any of these pressures, it would have been quite nasty, because you have to have to the power of, okay, in this case not nasty, to the power of gamma over gamma minus 1. But in this case, we just don't have to care about anything. We can just write it in the way it is, which makes it really nice. And
facilitates laziness.
Exactly.
Yes.
And laziness is something I'm good at. And also, which is really nice about the system is you don't have to care how you write in which order you write your equation. So there does not have to be any way. For example, here, the inlet P and outlet P is defined here. But what the values are, well, I don't know. We haven't calculated them yet. But we can still use this equation to calculate it. And of course, for our valve, we also want to have a nice symbol, because I really like symbols. I forgot the stuff which we got made at the course. I made really nice systems. But this is a simple valve. So it makes it easy. Let's go for white. You can choose whatever color you want. So that is now our basic valve. And going back to the presentation, what we just had is we talked about prepared a basic class for inheritance. And that means, so what we had, the basic valve is a base class. What we can do now is build on. The base class in our case contains the enthalpy balance or temperature balance and the mass balance. What is still missing is our pressure balance. And for that, we can just extend our basic class to our next model. And that is what I'm going to do now. So we have here our basic valve, which is a partial model. And then you can just new extend from. And let's call it simp valve. In this simp valve, if you go in the equation window, you can see extends basic valve. So all variables which we defined beforehand in our basic valve are also existing in the simp valve. And what we have to define here now as a parameter is just our pressure drop coefficient, which makes it, kind of simple and nice. And for this one here, based on the equation and the definitions I had, I think this value makes sense to get a decent pressure drop. And what we want to derive right now here is just a simple pressure drop equation. And this was the flow equals to K times sine of inlet P minus outlet P times square root of inlet P square minus outlet P square.
Absolute value.
Ah, yeah. Thanks, Christoph. And the square root is small. So, now we have our simple valve. And I told you before,
Outlet P in the sigma function.
if I just take all the time I had like that, my neck would be not working anymore tonight, so I just right blind. So, if you recall, I told you we need as many equations as variables. And for that, we have a quite nice function which checks it for here. It tells you how it's working. It's currently here. It was on the other screen. It says, okay, the model has the same number of unknowns and equations, 4. Nice. And so it's no warnings, 0 errors, very nice. And what we do now is so-called aggregation. We defined now in total 3 different models. The one model is our inlet, then our valve, and the next one is our outlet. And we do want to aggregate all of these now together into one big flow sheet. And there is the point where Modelica has an advantage over the other languages, because in Modelica you can just drag and drop. And that is working like I define a new model, which I call comp. And in this model, I go now in this window, because here's all the submodels you're using. So we need an inlet. We need our simple valve. And we need an outlet. Okay. So now we have a combined system. We connected our boundary condition with our simple valve and can calculate the pressure drop. If we want to go for different inlet conditions that we had beforehand, we just double click here and you can change the parameters. I'm not sure whether you can see it with this contrast, but in gray, really low gray, it's a flow rate of 100, a temperature of 280, and here of 130 million. No. 130 bar. Screw it. 1.3 E7. These are the values which I gave it as initial values, but you can change it if you want to. And also here in you can see here the value 1E minus 4. So that is aggregating. But before we go to simulate, I will talk to you shortly about the last concept, which makes it really nice and why we define it as a partial model, and that is polymorphism. Polymorphism means we can easily exchange one model for the other and replace it. And in our case, that means that we define a new extended variable, extend from, we call it simp valve 2, just because I like that. And this simp valve 2 is exactly the same as the simp valve. The only thing which we change now, we do not define our parameter, but we define another input. And this input, I will grab myself from the Modelica library. So I go to Modelica. What was it again? Blocks. Interact. I don't know.
Sources.
Yeah, used to be. Yep. sources come afterwards. Interactions. Ah, screw it. I just copied from the other one. Oh, that's the other package here. Yeah. That was the lazy point of view, because I normally don't use other points because I'm only interested in steady state, and there you just don't need anything like that. What this one here is, if you double click, you can already see, okay, Modelica blocks interface real input. So essentially what it defines is a real input to our valve. The real input has a value k, which is essentially the same value we had initially in the equation. But we do not define it in the model itself, but it comes from outside. And so our simple valve is now, simple valve 2 is defined, and in this combined, we can here go to added attributes, replaceable, with a constraining clause, basic valve. And this constraining clause just means if we have a lot of models you don't want to change every time, or look, okay, what kind of, where is it in my package? But with this restraining clause, you just right click, change class, all matching choices, and you can go to the second one. So you can just replace it. Sorry, that is just really awful for my neck. And now we have the other valve where we can define an input, which makes it essentially quite simple. Okay, but we just, at the time being, we only went for the model, and what we're interested in now is the simulation. In the simulation, we have first the translation, it is really small, and then the simulation. And that is really not important to understand, because you start with the Modelica source code, which I presented to you. But the Modelica source code, as you've seen, has a hierarchy. So if you have a packet from somewhere else, it's really hard to find where it is. And what it does first is it defines a flat model, where you have a huge system of equation, which can be complicated, but does not have to be. And when it has the huge system of equations, it analyzes it, which means it sorts it in a way that you have exploit the sparsity of the system, and if possible, and then it optimizes it. Means a lot of relationships you do not need in your system of equation when you solve the system. You just need it into, for the easy, or that it's easier for you to build up your model. But essentially, they're always the same, especially flow variables. So all the inlet Q, outlet Q, if you do not have any change in flow, will be always the same. So they just kick it out. And as soon as you have optimized, you generate a code. The code generator is a C code, and you need, for Dymola, you need Visual Studio Express as a compiler. Because the C compiler just needs to get you your executable. And in the end, you do your simulation. And that is what we do with our simple model.
Do you have to convert it to C code, or can
It does it automatically.
Okay.
You don't do anything. I just go here back to my original variable, because we want to start with the simple valve. As you can see, I was all the time on the bottom right, you see modeling. And the modeling means, in this case, I write my model. And now I go to, which you don't see because it's cut off, simulation. And I have a lot of old code running. That is the general simulation environment. Here you can see plot variables, but in our case it's kind of constant, so it's kind of boring. You can see your results, and you can just solve it. And in order to solve it, I first changed the time horizon to 20 seconds. Already did. And then you go here, which is simulate. And it tells me now, in this window, in the translation, I have an iteration problem, but I do not have any start value, which is for our simple problem not a problem, for bigger problems can be. And in the statistics, we see that originally we had a 1-1 system, and after manipulation it goes to 1-0. So it simplifies our system. And in simulation you just see how long it takes. But what we see is we have, that is really small, a really, really small pressure drop, because my pressure was slightly too high. Let's go to another, because then it looks nicer. Simulation, simulate, compiling. Okay, we have roughly a 50% pressure drop, which is quite a lot. And our pressure drop also gives us simultaneously a temperature decrease from 280 Kelvin to 235 Kelvin, which means we should not use the equation we use for the pressure drop, because that is for isothermal, but it's not that crucial at the time being. And if this one here is a plotted pressure, and you can see the pressure of the outlet is always the same, which makes it kind of boring. However, what we can do, we now had a pressure drop over the valve because our flow went from the left to the right. We can also define it the opposite. So we can go for minus 1000. And if we then we have to translate it again, simulate it. What you can see is instead of a pressure of 63 bar, we are now at 164 bar. So for Modelica itself, it does not matter in which direction the flows flow. You just define it in the way you want to. So you can model easily reverse flow, which makes it, in my opinion, quite nice. But we had also another. Where's my mouse? Yeah. We had also the other valve. And let's go for the other valve. You can see here we have a real input. And the real input needs a value which we can use. We can use a constant value, or we can go up here. Shift that. And use, for example, a step function. The step function is just part of the standard Modelica library for free. You don't have to code it yourself. It's quite extensive what you have there, but I like to have my own models. And you can see here, where did I put my mouse again? We can, again, as beforehand, simply connect it. Hope that it's connected. Yeah. You can see here with the connect equation, inlet outlet is with simple valve inlet, simple valve outlet is with outlet inlet, and step Y is with simp valve K. And that is essentially the connection we have just made. Let's make it look nice. And here in this step function, we can define the height of the step. Step is actually kind of boring. Let's go for a ramp. In the ramp function, you can define the offset. And the offset is in the ramp the initial value. So we want to start here again with 1e minus 5. The height is the height of the ramp. So if you start at 1e minus 5 and you have a height of 2e minus, no, if you start at 1e minus 4 and you have a height of 2e minus 4, you end up in the end at 3e minus 4. Let's just set it to 2e minus 4. The duration is just this part here, the length of the ramp, let's say 10 seconds.
I guess you want -4 in the 8.
Yeah, I want. because in the end we don't have any pressure drop. And we have a start time at 5, just to see how it behaves initially. Okay, let's check again a bit whether it's working. Same numbers as unknowns and equations. Nice. Simulation. Simulated. Here you can see we start at the 1e minus 5, and then we have our ramp. As we do not have a linear dependency of the pressure drop as a function of k, we will have this nice shaped system, which I really like the shape. But that shows us the pressure drop of our inlet pressure. And also the temperature behaves quite similarly. You have the change depending on the pressure drop. And that is how you can, even if you have a steady state model, you examine your model for multiple different values of parameters.
These are purely algebraic equations, aren't
Yes. You can, however, introduce as well differential equations.
they?
I'll come to that.
I don't understand this shape of this curve when you have a ramping without any dynamics in it.
The point is, I have a ramp on K, and this one here is the pressure. The inlet pressure is the same. However, the dependency of my outlet pressure on K is not linear. If the dependency would be linear, then I would get a normal ramp, but it's not. That's why I get this shape, because it's not a linear function.
Okay.
It's a kind of a weird function to get. You can also implement in Dymola or in Modelica in the language, you can implement without any problems differential equations.
Yeah.
And it can work with mixed integer nonlinear problems. So the algorithms are there. I'm not using it because I'm more in steady state optimal solutions interested, and for that it's just not important to have any derivatives with respect to time. Okay.
Okay.
Okay, let's continue. You see, we just defined our own package. We used parts of the Modelica package, but there are way more packages available. And they're either free packages, which you just download, open source based, or public license based. So that makes it quite easy. There are also commercial packages. For example, the company where we did our Modelica course, they sold a thermodynamic package for refrigeration cycles. So their whole task is around selling their package, or their whole job, and doing Modelica trainings. And as said, there's the Modelica standard library. There are packages developed by universities and companies. The companies are normally quite, they do not want to get their packages out because it's their own intellectual properties. Universities are there way more open-minded. And packages developed by individual users. For example, if in the subpro, the one working on his gravity separator can build a package around for the gravity separator. And someone else working on whatever, I don't know what is included, he can just make his package, and you can combine both packages to connect the gravity separator to whatever. So it makes it quite neat. However, you still have to define always, if you want to have it really nice interchangeable, stuff like connectors should be defined over all packages the same way. Otherwise, you can get problems by connecting different packages.
Do you use Modelica and Dymola also for steady state simulation?
You can, but I come to that. There is a really nice overview of packages on the Modelica webpage. When the presentation will be uploaded, you will just have the link. That makes it way more easier. As nice as Dymola and Modelica sound, there are some problems. I have encountered a few problems during my time with it, and sometimes it was quite nasty. If you have steady state models, non-dynamic models, you can use Dymola perfectly to model it. However, the initialization is quite nasty. And that is one of the problems I faced, and which makes it difficult. But I think that is not a problem of Dymola, that's just a problem of steady-state models. But in Dymola, to define starting values is not the nicest way, because you have your full model, and that is translated afterwards into a simplified model. And there you just don't know which variables it uses. Second problem is with the Dymola, it cannot handle PDEs. So if you have to model PDEs, Dymola or Modelica is not the language you want to use at the time being. It's constantly updated, but at the time being, it cannot handle PDEs.
Yeah, but usually you semi-discretized PDEs anyway.
You can, that, exactly. Depending on the software, it can be quite costly. We just checked it out for Dymola licenses, and that is way higher than whatever we know about any other language license. It's probably because they don't sell so many licenses, and that makes it expensive for them, but it's still quite expensive. And what I personally don't like is that you have to predefine all variables. So if you want to use something which you have not defined, it's not working. It's directly an error. Okay, more information is just this one here is a really nice graphical interface, which I will show shortly to you. And there you can see if you have the most general functions, it just gives you a short explanation and then a reference to the Modelica specification, where you then can read through it in detail. And also this ebook or book, which is available for NTNU users, is a quite nice book to go through Modelica. And to finish off, I just want to show you what I work with. This one here is just my package which I designed for a simplified ammonia loop, consisting of valves, compressor, heat exchanger, simple separator, and everything together. This one here is set in an unconnected manner. So we have just a normal compression train with interstage cooling, recycle coming in, heat integration around the reaction section, cooling, recycled purge. Also existing in a connected manner. The unconnected is just the stages how I develop it. In total, this system has, it's on the wrong side again, 1,245 equations and variables, which is
Dynamic equations? Or
no,
is it-
all steady state,
But the reactors are, they are
CSTR cascade,
CSTR.
cascade.
We don't have the gradients. Okay.
The reactors are modeled as simple CSTR cascades because we want to have a one-level system. We don't want to go to multiple levels where we have to solve in each. If we use it for optimizations, we don't want to solve a differential equation in each optimization step. And just 1,245 equations. If I go to simulation, the translation takes a while because it tries to find a simplified version of it. Conflicting starting values. Yeah, that is because I specified my starting values, because I have to do that here, otherwise it does not find a solution. And the interesting stuff is, initially 1,245. Original model, I don't know how they exactly count here, but from, for example, constants 111 scala, it just reduces it drastically. Where was it? From 668.11 to 282.00. That's just the sizes of the nonlinear systems of equations. Initially I had 3, with the biggest one a size of 668. Now I have the biggest one of a size of 282. And that is done by the translation section. And I hope it simulated it correctly. Yes, it did. And if we want to see the ammonia outlet flow, you see here we do not have any values standing. The point is, because it's dynamic values, I have to specify the time. You can see 99.08% pure ammonia, 825 moles per second at a pressure of 138 bar. So it's working also for bigger models, but you can get the slight problems, and it can get a bit annoying. Okay. Then I would like to thank you for your attention, and I see the pizza is carried in. I hope I could somehow bring the Modelica language a bit closer to you, and yeah, start interest for you in the language. Thanks for the attention.
Thank you, Julian. Thank you, Julian. Does anyone have any pressing questions, or can you just take them up personally with Julian?
Maybe. Modelica is a equation-oriented simulation language, isn't it? You solve all the equations simultaneously. Yeah. And that's the reason why I think also it's difficult to converge
Steady-state solutions?
Steady-state solution. You
Exactly.
have a good guess of the initial guess in order to have a convergence.
Essentially, if you have a steady-state system, you just have a Newton-Raphson solver to find your zero of the equations. You need a good guess to solve it. So that is essentially the problem of all steady-state software. However, steady-state software or equation-oriented have a huge advantage if you go for modeling of complex systems, or for optimization, put it this way. If you get an initialization point, then the optimization goes quite well.
Anyone else?
Can you export, for example, your model to another software like HYSYS?
HYSYS, I cannot say. I don't like HYSYS. I also don't like Aspen Plus. I don't like Aspen Tech, and I think they make the equations, the software not really better in the last 4 years. However, you can export from Modelica to different software, and that is with a so-called functional mock-up. And with a functional mock-up interface, you get a code which you can export, for example, from Dymola to another software. Like Simulink is working, MATLAB is working, HYSYS, I don't know. But as you can export it to MATLAB, you can also connect it with spreadsheets to HYSYS. So that is working. Whether you can directly import it, I don't know whether HYSYS supports the FMI, FMU standard. But for a lot of different software, it's working.
Maybe you can figure it out and then come back and do a lecture next semester on it. Okay, guys, I think that's it. Thank you, Julian. That was an excellent presentation. I myself feel like I can start Modelica at this point. I can make a valve. So, all right, everybody, get some pizza, have some drinks, stick around, chit-chat, get to know each other.